he shows exactly how he solves it in detail and all the calculations, and so you can follow what he does very, very easily. Right? So every solved example in the book, I assign every solved example in the book to do as a question. The final example, midterm exam, is very similar to the examples that solved in your book. All right, now example on page 316 is obviously one beam that is fixed to the wall, and it says find the internal reaction between C. So what should I do? Choose a system that is kind of like conic, right? Yeah. As I said last class, you used to take the entire part as system vector statics to find the external reaction. Now we've just changed my system to be either this part or this part, because I have two possibilities, right? For a section, I have either right or the one on the left. Then there are the next part is run FED, write equation, solve, and verify. And the interesting part is it really doesn't matter if you take system 1 or system 2. The one on the right or the one on the left. You should get exactly the same result. Right? So let's first take the one on the right. So if I take system 1, I'm going to get something from my FED like this. So I'm going to distribute the load, the triangular, distribute the load, and at this point, I do not have the height, right? That's what I need here. I do not have the height. So what should I do? Well, I have the total height, and since this triangle is similar to the big one, I can use the law of proportions to find this h, and then I put it here. So let me draw the system 1 and 2 FPD simultaneously instead of just considering system 1. So this is system 1, and this is going to be system 2, and this is fixed, right? So for system 1, I'm going to get the distributed load like that, and this is just h, and I don't know it. And this is going to continue like that, right? And I know this is 270 right here. And again, this is h. And then I'm going to have the shear load V at C, the moment M at C, and a normal force N at C. 3 components here. And that's pretty much all for my system 1. Why? Because the beam weight is only surface weight, right? The body force for beam is gravity, and we assume that the beam is very light, right? So I don't have a gravity. If I had gravity, what should I do? Put it at the center here, right? But I don't have gravity. Now for this guy right here, system 2, you already have the distributed load, right? And then you have the load here, AY, AX, and MA. 3 components. Why do I have 3 components at A? Because it's fixed to the wall, right? You can't move it in the X, you cannot move it in Y, you cannot rotate to the wall A because it's fixed to the wall. So you have 3 components. And then the rest is nothing except the opposite reaction, NC, BC, and MC. Just the opposite of whatever you have right there. You put it here. And that's all. That's FED for system 2. Right? So what my purpose right now is to find these guys, these 3 components. So as you can see, I can either use this system or this system. Which one is easier? System 1. Right? Why? Because if I want to do system 2, first I need to find the external reaction, AX, AY, MA, right? That means first I should take the entire big thing as system, find moment, and axial and vertical load here, and then solve for MC, NC, and VC. So I choose this one because it's easier. But because before I actually want to find here, I have to find my H, right? So how can I find my H?
We set up a proportion.
Proportion between this triangle, right? So you say in the small triangle, let's write it here. So you have two triangles right here. This one is H, right? This one is 270. From here to here is 6. Right? The entire thing is 9. So we can say this small triangle is similar to the big one. So you say H over 270 is equal to 6 over 9. That will give you H is equal to
180.
180. Double, huh?
Could you simplify the distributed load before?
Yeah.
Okay.
Yeah, you can do that. But first, I want to find how much the distributed load I have here before I simplify it. Right? So first you have to find your H, and then you say, well, I will place the simplified load at the centroid, and then you have all unit load or point loads.
Well, I guess I'm asking, can you simplify it before splitting it into sections?
No, you can't. Well, the thing is, that's a good question. He says that, can I just get rid of that and put it one point load at the centroid before I cut it? And the answer is no. Why? Because we used to do that for external load finding. Here, because the loading is distributed on every single point on the beam, you can't do that. If you replace that with just unit load at this point, then in fact you are telling me nothing is here. But in the real physics, you have forces here, right? So you have to include a distributed load when you section, like the way I did. Now, here in this problem, you are finding external reaction, right? In this particular thing, the internal loading on the big beam is external loading on system 1 and system 2. Now here you can replace that with point load. So whenever you want to find external loading on your system, not internal loading, external loading on your system, then you can replace the distributed load with point load. You see, these are external loading on system 1, external loading, system 2. But they are not external loading for the big things. Right? So here I say H is 180. Assuming the computation is right, double check the computation. So now I'm ready to replace this triangle with the one load at the centroid. So where is the centroid? 1/3 of the base. How big is the base? 6. 1/3 of 6 is 2 from here. 2 meters. And the value is 180 is from here to here. The value is the area under this triangle, which is half of base 6 times 180, which is equal to
540.
540. Assuming the computation is right. So here I want to find BC. What should I do? The shear load. Summation of force in Y. First, let's write all the equations for this system. How many equations do we have? 3. Summation of force in X0, summation of forces Y0, summation of moment about any point must be 0. So let's expand the first equation. What do I get? Negative NC right here, right? This is moment, doesn't do anything with the force equation. This is force, but it is in the Y, right? It's in the Y, so that's all I have. Is equal to 0. So the axial load is 0. And it makes sense. Why? Because I don't have any physics or mechanism that put axial load compression. Right? Now I'll go to this guy. BC, positive, goes upward. When we say positive, negative, we usually consider this system, XY, by default. Right? But some of you guys have already done work with AutoCAD or SolidWorks, right? When you look at this, when you draw something by default, your XY is like that. But you can always rotate your default system. That means you can always draw a different system. You can rotate it so X becomes this way, Y becomes this way. You can also make it with some angle like XY. So that means you can always change your reference system. When did we do changing reference system like that in vector statics? When we did friction of mass like over the wedge. You remember when we had a wedge and we had some mass over here, right? Yeah. And then we put the system like that. So the orientation of system is along with the forces. So it simplified the equation, it decouples the equation, right? So when I say summation of force, I'm talking about this default system. So in the Y, this is positive. So BC positive, nothing about NC, nothing about MC. This one is negative. Negative half of 6 times 180 is equal to 0. Right? When should I choose? For a moment, what was the strategy to choose a reference point for moment equation? We should choose a point for moment equation to eliminate as many as unknowns as possible. Right? So it should be C. So I replace this sub with C. That gives me the fastest way to solve the equation. So if I want to do that, what do I get? I get MC, positive or negative? Negative. Negative. And then you go to BC, nothing comes from BC, nothing comes from NC, right? And finally you go to that, which is 1/2 of 6 times 180 times 2. This distance 2 negative. With negative is equal to 0. So now, what was the next step? So we choose system, FVDs, equation, solve, right? So if I want to solve this, well, already NC is 0. Put this one in calculator, VC is equal to 540 newtons. And the moment, bending moment is equal to 1080 Newton meter. And it's negative or positive? Negative. Put it in the calculator. Make sure to double check the results. Okay, so that's the way you solve it. Now I give you an optional homework when you go home. Try to choose this system and solve for NC, VC, MC. Right? So what do you need to do first of all? You need to first take the entire thing as system and find the reaction here. Right? That means first you need to find AY, AX, MA. And then if you take these as a system, what should you do to solve for MC, NC, and VC? You should replace these two loads. You should break it down to a rectangle and a triangle, right? And replace these two loads with a unit load. So you're going to have one load here and one load here. And then do the same thing, write the equations, and then you find MC, NC, VC. The value of MC, NC, VC must be exactly equal to these three terms. If it's not equal, what do you do if it's not equal? Try it again. That's a good practice. In fact, that's a very good practice to match the right with the left, right? Now let's go to another example in the book. Example 7.2. It says find the internal reactions at point E, right here, at this point. Find the internal reaction at point E. So what should I do? Somehow you should cut it, right? And then do whatever we did to make the static 5 steps. So, if I want to cut it like that, like this, then I'm going to get three possibilities, right? Let's say system 1, system 2, system 3, right? So, I make some planning before actually I write the equation and solve. Well, this is easy. Why? Because I only have one unknown tension, so I can immediately solve that, put it here. In fact, my main thing is system 2. So if I have tension here, then I would have 3 components unknown here, and then I'm going to have one unknown here, tension in the cable. So can I solve it for unknown per system? No. So what should I do? Before I do that, it's better to take the entire beam as system, right? And find the external reaction. 2 here, 1 here. How many unknowns do I have? 3. 3 unknowns, 3 equations, because I have one system, right? Once you get these unknowns here, then you can go to system 2 and write the equation and find 3 components here. So before I solve this guy, right, before I go to system 2, I take the entire thing as system, including this mass, right? So I want to draw, so let's call this system 0, the entire thing. So I want to draw a feed for system 0. What should I do? So this is the main. This is my system 0. And there is a mass here, right? This is my system 0. In order to draw a FED, you say, I walk around the border, find surface forces, and then I put body forces, and then I'm done. So for surface forces, let's start walking from this point, right? The first point you call the, here you have AX, AY. Do you have a moment?
No.
Why? Because this is just a pin. AX, AY. Then you continue walking. Then you cut this cable. How many force and moment do I have here when you cut this cable? 1, right? And it's always tension. So you put something like T. Let's call it T. Then you continue walking. You're not cutting anything. Look, I'm not cutting this cable, right? So you're not cutting anything. So there is no surface forces, right? Continue. And then you come back to the start point, right? So that's my surface forces. This is all I have for surface force. Do I have body force? Yes or no? Yes. Why? Because I have mass here, like here. So where should I put my body force? Right there, here. So how much is the body force? 500 times 981. Right? So what's my objective? To find T. Right? Why do I need to find T? Because when I go to system 2, right, I have this guy, so I find these three components here. What I'm saying, you've got to make some planning before you solve it. If you don't make plans, you don't have enough time to solve it. Right? So how can I find T? What's the fastest way to find T in this system? Moment? About? Thank you. Summation of moment about? A is equal to 0. Let's expand this equation. Let's start with AX. What do I get? 0. 0. Then you go to T, right? Before you actually want to find the moment come from T, you have to break it down. X and Y. So first you have to find this angle. Let's call this angle theta. How can I find theta? Tangent. Theta is equal to 1.5 over 2. So theta is equal to arc tangent the calculator arc tangent 1.5 divided by 2 is 36.9. So let's write it here, 36.9. So when I do moments, right, this 0, 0, here it's going to be T times sine 36.9 times moment arm. What's the moment arm? 2. Positive or negative?
Positive.
Positive. Right? Now you go to this guy. What's the moment come from this force with respect to A? Right? So what he said this force, in fact, we move it up, right? So this distance times this force, right? Which is equal to
4,905.
yeah, let's write the value. So it's 3 times 500 times 981. Right? With the value negative. Right? Is equal to 0. There is nothing else. These are only sorts of moments. Right? Solve for T. Then you get T is equal to 3 times. It's 12. Well, I have one system, 3 equations. Summation of force x0, summation of force y0, summation of moment at any point 0. These are in system 2, right? These equations here were in system 0, right? Big one, the system 0, right? So here, if I expand the first equation, I get negative NE. And here, the interesting thing is the axial load is not 0. Why? Because this angled cable is going to make some sort of compression for me from here to here only. You see the axial load is not zero from only here to here. What about from here to here? The axial load is zero. Why? Because if you consider a system like that, there is nothing here that causes compression or tension. Now later we talk about diagrams, moment diagrams, shear diagrams, axial load diagram. When you draw the diagram, we have a non-zero here and then zero here. Later on we do that, yeah.
Couldn't we just completely ignore system 3 for the most part instead of solving all of that?
No, we actually ignore system 3 in this case. Why? Because we can first take system 0 to find the T, and then we can take system 2 to find all the 3 components.
Well, couldn't we ignore system 3 to find tension also?
The system 3 doesn't have anything with the tension. Well, the thing is, if you consider system 3 from the beginning, first you need to solve for AX, AY, external reaction. So somehow you should go to the bigger picture and find tension AX, AY, like the way we did it in system 1, right? But here, we don't really need to use system 3, right? We use system 0 to get tension, and then we go system 2, system 1 to get, system 2 to get all the AX, all these components, 3 components. Now, when you go home, it's a homework. Take system 3 and solve for those 3 components, ME, NE, and BE. You must get exactly the same result, like the way we did in the last example, right? So here, expand this equation, you get NE with the negative sign, negative 12 times 25, K cosine 36.9 is equal to 0. First equation. Second equation, you get V, VE positive, and cos 12, 25K sine 36.9 negative 500 times 981 is equal to 0. Now finally you go to moment equation. What's my reference point to write the moment equation? E. E, right? Why? Because you want to eliminate as many unknowns as possible. So you say M sub E. Right here. So you get NE negative, right? Nothing from these two guys. What about 12.25K? And multiply by sine 36.9. Then you multiply by this distance, which is 1, and that's going to be positive. And finally, negative 500, 981 times 2 with negative, right? Is equal to 0. Now finally you go and solve it. If I solve the first one, what do I get for shear force? The normal force is equal to the calculator is a negative number. Yeah, negative 9.8 K. Negative 9.8 K. And then, why is negative? First, before we solve the rest of it, meaning of negative positive. Look, when I choose here, the tension is positive. This is tension default. So if I get negative, what's the sign? The other way. That means it's compression. Why is compression? Because this cable, you see, when you put this load here, this cable causes this part to compress. You see that? If this cable was hanged in the other side like that, it would be tension. You should get positive. So it makes, when you remember we had this last step, verify. This was the fifth step. So system FPD equations solve. So when you, the last step was verify. When you want to verify, you have to always ask this sort of questions based on intuition, because most of the time you don't have solution manual, right? You have to go after your intuition. So now let's solve the second one. The second one is going to give you shear force. V is equal to, are you sure?
Yeah.
500 times 81.
2000.
So it's negative 2.45 K. Negative 2.4. Well, in the exam, if you get like negative 2.4, that's fine. Even negative 2K is fine. Now, finally, you solve the last one. The last one gives you ME is equal to negative 2.45 kilonewton meter. You sure?
Yeah.
Or this one? All right. So now you see that the internal loading is in fact nothing new, except we just change our system, right? It's like we are just doing vector statics. It's nothing new. So now I want to solve. I want to go to the next topic, which is stress. The stress analysis. We have several meanings for stress. The first meaning of the stress you're pretty familiar with. It's some sort of anxiety, right? And in the modern age, the machine world, we all have this problem, anxiety. But when we say stress in solid mechanics, what do we mean by stress? It is some sort of anxiety, but not in us. In the material, right? So you can say that when, for example, if I have this column and fixed to the roof and I apply some force F, well, what happens to this guy is going to extend. It's going to shrink a little bit because mass is conserved, but instead the length is going to increase. Right? You know the conservation laws. The mass is conserved. That means if this one guy wants to extend the length, it should shrink the volume. Otherwise, there is no way that keeping the same volume would also extend. There is no way to do that. Unless you have a cavity here, right? So this is what happens here. So this is going to extend with the amount of delta. So now you know that when the moment you apply this force, this guy is in stress, right? Some sort of anxiety. So the stress in solid mechanics is related to the amount of force you put. So the stress is related to proportional to the amount of force. And that's what our intuition tells us. When you put too much force on something, it gets more stress. Now, consider the cross-section area here. When you cut it here, this has, let's say this has a circular area. When you apply force like that here, then you, in this area, then you have a little tiny distribution of force everywhere, right? Like that. At any point, let's say this point. BA, the small, tiny differential area, on this cross section. The moment you apply force, it's going to be, you're going to get the distribution of forces here. And if this force is far, far away from that, this distribution is uniform. It's just constant. Near this point, your distribution is like that. You see you have more forces here and less forces here. You see that? But when you go away from that, you get uniform. That means everywhere here, it's uniform distribution of force. Right? So, another thing I want to say, the stress here, assume that you have a big area. The bigger the area is, the smaller the stress is. Right? So stress is proportional to the inverse of area. Now, somebody defined, say, well, this, you can convert this to equation. Sigma is equal to F over A. And then take the constant, and this is fixed to the wall from the top, and then you have the weight 500 kg hanging from this point A. Now we want to find the stress at this point, far, far away from that. What should I do? You remember I said you need these 5 steps in your life. Wherever you go, it's always these 5 steps, nothing new. So let's go to system. What part should I choose as system if I want to find the stress at this point? Well, first of all, before I find the stress, what do I need to find the stress? The force, because I have the area, right? The area is, cross-section area is given, the radius is given, so I need to find the force. So if I want to find the force here, what should I do? Choose the system. So what part should I choose as my system? I choose this as my system. Now you draw FED. Let's draw FED. If you draw FED, then you get how many force and moments do I have here? 3, right? But we know that we don't have any side effect and any bending moment, right? So I can eliminate the moment and the force in the X. So I only have one force component in the Y, right? In fact, I don't have one unit point force. It's going to be something like uniform loading force, right? Which I can replace because it's external analysis. I can replace it with just one point at the center, like that. That's my force. Now you continue walking on the border. What else do I have for my external forces? External loading. The surface. That's the gravitation, the body force. What do I have for surface force? Nothing, because I'm not cutting anything else, right? The only point you cut is this cross section. There is nothing else, surface force. So these are our surface force. What about the body force? Then I have body force, right? Where should I put the body force? Right here. And the value is 500 times 981, right? So I can find F by just one equation, summation of force in Y. So F is equal to 500 times 981, which is equal to
4,900.
is equal to 4,000, right? 4.9 K, almost, roughly. Then you say the stress, the question is asking for the stress. The stress is equal to force which is 4.9 K divided by the area. What's the area? Height, radius square. What's the radius? 2 centimeters. Don't forget, when you put Newton here, you have to have meter square, not millimeter square, not centimeter square. One problem we have in the lab is the student does everything correctly except this unit conversion. And then you see very big bad results. The error is like 200%, 2000%. The error is like 2000%. And then when you fix the unit, the error becomes 2%. It's all come from the unit conversion. So you say pi times radius. Radius is 2 times -2 centimeter to meter square. Don't forget, 4.9 K. What does it mean? Times 1,000. Put it in your calculator. Don't put 4.9 divided by that. Again, you get another unit conversion problem. Now let's put it in the calculator. What do I get? $4.9. You get 3.9 to 10 to 6. What's the unit of that? Newton per meter square. Now, there is another thing I want to say. Newton per meter square, that's what we know, right? Because this force is Newton, area is meter square. Somebody tried this for the first time, and he was a French mathematician who did hydraulic gas and things like that, and his name was Pascal. So they call Newton per meter square, they call it Pascal. If you don't say Pascal, that's fine for me. Otherwise, you just say Newton per meter square. Right? Now, the thing is, as you can see, this is a huge number. 10 to 6. Right? So the way they say, instead of putting 10 to 6, they say M, mega. And instead of that, they say PA, Pascal. So you see MPA. And when you see MPA, they're not talking about fuel consumption or something related to that. They're talking about megapascal. And don't forget, when you put this in calculator, so in fact I have 3.9 MPA. When you put this in calculator, you have to put 10 to 6 too in your calculation. Don't forget that M is mega, right? So I want to ask another question. Why do we do a stress analysis? Why we simply don't use forces like electrostatic? Why we do stress? So this is one quick one. You can answer that.
Doesn't consider the internal forces, like all of them, on the whole area, if you're just applying the one force. So if you consider the stress, you get the whole picture, basically.
Okay, not a complete answer. Yeah.
I would say if we're using material and we know what stress is required to cause that material to break, we can analyze how much we're on and see the breakdown.
That's right. Email me for quick one. And I forgot your name.
Sorry?
I forgot your name.
James.
Last
Good one.
So, in fact, this is what we need. You see, you solved vector statics, and it was all addition of 2 vectors, mathematics, cross product. We didn't like it. And then we went to force analysis. We said, well, okay, let's say I want to find the force here in this structure. What do I get? Well, the end result is you'll be able to do a stress analysis. Why? Because every material we have in engineering, they have a limit stress. That means if, for example, if this is aluminum, right, there is a maximum stress. That means that there is a maximum limit for this force that you can apply tension. Then after that, it's going to break, it's going to fail. And what, as an engineer, we don't want material to fail. That's the ultimate purpose of engineering design, right? So, in fact, for every material, we have a maximum stress. We call it sigma max, right? Sometimes we call it sigma, we have ultimate. After that, we have failure, right? And this depends on every material is different. Like for aluminum, is smaller than the steel, right? So that means that if you, now you can see, you can connect all the dots that since we started doing vector statics. If you are able to do force analysis, then you divide by area and do a stress analysis. And then if you do a stress analysis, what can you do? Compare to maximum possible stress. And if you fail, what do? You can loop back and change your structure, right? The configuration such that you get the smaller forces. And if you get a small forces, you get a smaller stress, such that at the end, you come to the limit of allowable stress. The limit that the stress is valid. It's not greater than maximum stress, right? That's called engineering design. In fact, the design completely depends on analysis. Design is simply a loop, an iteration of different analysis. So you choose a structure, your configuration, you do analysis, you find forces, you divide by area, you find the stress, and then you say, well, my stress at some point in the structure is exceeding the maximum stress. So what are my options? To either change the material, to put a more stronger material, or change the structure. Add more components or do some different kind of plane so that your force becomes smaller at that particular point, the critical points. Now you can see that this stuff, they make sense since we started doing vector statics. And it makes sense that we spend a lot of time on doing moment computation, right? Cross-product moment computation, which was the mathematical subject. Now it makes sense because, well, all those things, they result to find the force and moments, right? And if you find force and moment, you can find the stress, and then you can find stress, you can design. You can check if you are smaller than.
Yes, my experience buying video equipment. I can't wonder how long the mobile lasted before they just threw that thing out. I do that all the time.
Now the questions are like this in this course. They give you something like that and they say, does it fail? If I put 2K, force 2K, let's say Newton, and these are two bars, one made of aluminum and one made of carbon steel, and they sound sort of like welded or connected here together. You see that? And they're fixed to the wall. Yeah.
For quizzes and tests, will we have like a chart that says like the maximum
That's
stress?
good question. Good question. Yes. This maximum stress, sigma max, is gonna always be given to you. So for you have a chart like always, I give a chart like aluminum and steel, like high carbon steel, some sort of variation of the steel. And then you have sigma max here, sigma max. And also we talk, next class we talk about things like safety factor. That you should consider also additional margin because the analysis is not good because of something called the stress concentration points. The analysis of the stress you do is not very, very accurate because we assume the stress is uniform per cross section. But in the real physics it's not uniform, it has some variation. So at some point you exceed at the stress that you compute. So you have to put additional margin, it's called safety factor, we talk about that. But right now, roughly, I'll put the force 2K here, and I say, well, I give you this data on maximum allowable stress for aluminum is this, for stainless steel is this. Does it fail or not? Let's say for steel is 200 gigapascal, and for this is 87, for example, gigapascal. Example, this is like example roughly. Now you compute to see if this is going to fail or not. So what should we do? Again, come back here. So what's the plan right now? Huh? Yeah, you actually choose two systems. For example, you can take one system like that, excuse me, and then you can find the axial load here, right? And then you choose another system like that, then you can find axial load here. Once you get the axial load, then what do you do after you find the axial load? You divide by area, then you find the stress, the actual stress that is at any point here. You find the stress here, you find the stress here. Right? And then you compare it with allowable stress. If it is smaller than that, what do you have? It's not going to fail. Right? If it's greater than that, it's going to fail. So let's do that. So if I choose this system, and draw FED, I'm going to get something like 2K. And here I know that I have axial load, shear, and moment. But you can see that I don't have any mechanism that causes the shear, right? The loading on this structure is purely axial. So I can eliminate shear because it's zero. If I write summation of force in Y, what do we get? Zero. V0. What about bending moment? If you write moment equation about that, you get zero. So this also zero. So that's your N. So what do I get for N from here to here? N is equal to 2K from here to here, right? Now what about from here to here? Now you take this system, let's write it, then you take this system like that, 2K, and the same thing, right? So N is still 2K from here to here. So if N is 2K from, let's put some weights here, put some length here. Let's say this is 1, and this is 1. So N is 2K from 0 to 2. From 0 to 2. The entire composite beam. Now you may say, well, then the stress is same if the axial load is same. Is that right? No, because the stress is equal to force over area. So the stress, you can say the stress is same from here to here because both force, axial load and area are same from here to here. And also it's going to be same from here to here. But it's going to be different from here to here because the area is different. So let's find the stress here. Sigma aluminum is equal to 2K divided by I 1.5 square. This is square, so here is equal to 2.83 mega Pascal. What about the stress here in the steel? Sigma steel is equal to 2K over pi the radius function. Now you tell me, is it going to fail or not? It's not going to fail. Compare it with that. In the aluminum region, it must be 87 gigapascal to fail. Let's say. Aluminum is like 1,000 times less than that. So it's not going to fail. Go to a steel. It should be 200 gigapascal. What do I have? 11 megapascal. Way less than that. And look, mole weight is 86 times 9, 81. It's roughly 800 something. So 2,000, it's like 3. This load is like 3 times of my weight. So if a guy, like 3 of me hanging from this column is not going to fail. If the thickness is like this big. And it makes sense, right? It makes sense. If you have material, aluminum steel, it's not going to fail easily. Yeah?
Does the welding affect it in any way?
The what?
The welding? Like the area between the two materials?
Yes. In fact, this point is called the stress concentration. So we made the assumption that the stress is staying here, right, uniform, like that. And then it's also uniform here. But you will have a jump. So you have something like this, and then you have a jump. But in the real physics, it's like, so you have overshoot here. When you reach here, the stress is not uniform. You get like that. So if you go use this software, I may give you extra bonus for using SolidWorks or ANSYS to model this with the finite element software. When you see here, you have an overshoot, and the stress can go twice or maybe more. We can go to the next level course, a graduate course, then you do a stress analysis, a stress concentration analysis. And what, as an engineer, what we do, because those equations are very complicated, we have charts. So depending on type of connection building, you have a stress concentration factor. So you compute the linear computation like the way we did here, and then you multiply by a factor depending on that kind of connectivity. And then you get the accurate, the one that we get from quantum element software, like ANSYS or SolidWorks. Right? So that's enough for today. Next class.